Hello everyone and welcome to the lecture video on elimination reactions part 3. Okay, we're going to start by talking about the kinetic isotope effect. So this is the section in your book that was introduced, I believe in edition 3, so you might not have this section if you have an earlier edition of the book, which is okay. I think this introduction will be sufficient for you. But the purpose of this section is just to give students an appreciation of how we've come to know about the different mechanisms that we've been learning in this chapter and depending on the book, chapter 7 or 8 or just chapter 7. So when we're studying mechanisms, one way that we can study a mechanism is to replace, for example, an atom such as a hydrogen atom with its isotope deuterium to see the effect on the rate of a reaction. If the rate is affected, then it is likely that that particular hydrogen atom that has been replaced with deuterium is in the rate determining step. So it is being removed, or that proton transfer is occurring in the rate determining step. So when we say a hydrogen, we're typically talking about the major isotope of hydrogen, which is just one proton in the nucleus. But there are other isotopes of hydrogen, for example, deuterium, which is a hydrogen atom that just happens to have both a proton and a neutron in its nucleus. So it doesn't really affect the electron flow because we're talking about a change in the nucleus for different isotopes, but it can still have an effect on bond strength, which can affect the rate of a reaction. So the other isotope of hydrogen that we'll be referring to, which is the one that has a proton and a neutron in the nucleus, will be referred to as deuterium, and we'll label that D instead of H. But don't get confused, that's still a hydrogen atom. It's just a different isotope than the most common isotope of the hydrogen atom. So it essentially has the same reactivity as a hydrogen atom, except for the fact that when its deuterium is bonded to carbon, it makes a stronger bond, which will have an effect on the rate if that bond is being broken in the rate determining step. So for example, if we're wanting to study what we think is an E2 reaction where the base is involved in the rate determining step, then we could replace the hydrogens that should be deprotonated with deuterium and see if there's an effect on the rate. And if there is a slowdown of the rate or a five-fold effect slowing down the rate, then that's an indication that that hydrogen is involved in the rate determining step. And this is known as the kinetic isotope effect. Right, so we talked about the fact that carbon deuterium bonds are stronger than carbon hydrogen bonds. Right, so if the rate slows down by a factor of 5 or more, then it can be concluded that the breaking of that carbon hydrogen bond is occurring in the rate determining step. So that's one way of analyzing the kinetics and learning about different reaction mechanisms. In this particular reaction, the E2 reaction was 7 times slower when the beta hydrogens were replaced with deuterium. So this is one of the reasons why we conclude that this reaction is a concerted mechanism and that the base is involved in proton transfer and the breaking of that carbon hydrogen bond or carbon deuterium bond in the rate determining step. Okay, the main thing I wanted to talk about though today is how we go about predicting products. This is going to be an extremely important topic, and it really sums up or wraps up everything we've been learning about regarding substitution reactions, both SN2 and SN1, and elimination reactions, both E2 and E1. So it's sort of, if you're just given the substrate and the reagent, how do you know which mechanisms will be in play, right? And so we have to analyze a number of factors. that will affect which products form and by which mechanisms. The factors are going to include the structure of the alkyl halide and also the function of the reagent. Is it going to react as a nucleophile or a base or both? Right? Is it considered a strong nucleophile, a weak nucleophile, a strong base, or a weak base? So those are really important as well. And sometimes we would also consider the solvent because we know that has an effect on the rate of different reactions that we've been talking about. So by now, it's probably clear that in many cases, a mixture of products will be obtained, specifically a mixture of substitution and elimination products are often obtained in a reaction. Of course, organic chemists never want a mixture of products. We only want one product. So reactions that produce only one product are considered more ideal than others, right? But oftentimes a mixture does occur and we would have to separate that mixture. So substitution and elimination reactions often compete with one another because reagents that can function as a base can also often function as a nucleophile. And similar substrates undergo different reactions. So for example, in this case, we have sodium hydroxide, which is a reagent that can function as both a strong nucleophile and a strong base, which is why both SN2 and E2 products are obtained in this particular reaction. We also want to analyze the structure of the substrate. This is a secondary alkyl bromide, which is a little bit slower for SN2 reactions. Recall that SN2 reactions prefer methyl or primary substrates, but it reacts well in an E2 reaction. So the E2 products will be major over the SN2 products using a secondary substrate given a reagent that can function as both a strong nucleophile and a strong base, such as sodium hydroxide. And then even when we figure out that elimination products will be formed in greater amount, often we still need to consider other factors, such as regioselectivity and stereoselectivity. Recall that elimination reactions often give Zaitsev versus Hofmann products, and so we would need to figure out which would be major. In the case of sodium hydroxide, it's a small, strong base, so the Zaitsev product is the major elimination product. It's also possible for some reactions that only one mechanism will occur. For example, even though sodium methoxide is considered both a strong nucleophile and a strong base, it's being reacted with a tertiary alkyl iodide. Recall that tertiary substrates do not undergo SN2 reactions. So sodium methoxide will not act as a strong nucleophile in this case, because if it did, it would do an SN2 reaction, and that's not possible on a tertiary substrate. So instead, it will act as a strong base and only give us an E2 product. Because there's no issue of regioselectivity, given that all three beta carbons are equivalent, there is only one single product in this particular case. So in order to understand how to use these reactions, right, to transform different alkyl halides into different products, right, one must be able to predict all the products that will form in a given reaction. So you want to predict all the products as well as understanding what will be the major and minor products. So how do we go about predicting products? Well, we can follow this three-step analysis. The first step is to determine the function of the reagent. Notice when I was analyzing those reactions on the past few slides, I started with the reagent. I talked about the function of sodium hydroxide in the first example and the function of sodium methoxide. Both of those happen to be strong nucleophiles and strong bases. So that gave me an indication that it might be possible to do SN2 or E2 reactions. So that's where we'll start, the function of the reagent and then what mechanisms those reagents will likely promote. And then the second step is analyze the substrate to determine the expected mechanism. So the structure of the substrate is also important. Is it a primary, secondary, or tertiary alkyl halide? Is it an allylic or benzylic alkyl halide? Is it any of those, but the halide is instead an alcohol? Right. So the substrate is really important because, as we know, for example, tertiary alkyl halides don't react in SN2 reactions, but they react really well in SN1 reactions and E1 reactions. So analyzing the structure of the substrate will help us determine the expected mechanism as well. And then once we've determined the expected mechanism, which could be only one, maybe it's only E2, right? Or maybe SN2 and E2, then we'll draw out all of the products given those mechanisms and consider any relevant regiochemical and stereochemical requirements, such as if you're doing an elimination, whether it's E1 or E2, will it be Zaitsev or Hoffman? And stereochemistry. Can you form different stereoisomers? Which one is the most stable stereoisomer? Is that the one that is formed? Or is it an E2 reaction that's stereospecific for the Z isomer? Those are all important things to consider as well when predicting the product. So remember, the first step is to analyze the function of the reagent, right? So you want to determine if a reagent is considered a strong nucleophile, weak nucleophile, strong base, and or weak base. So remember that strong nucleophiles promote SN2 reactions, strong bases promote E2, weak nucleophiles, because they don't promote SN2, by default promote SN1, weak bases, again by default, promote E1 reactions. So the following table is from the book, and it's a fairly good resource for categorizing reagents and the mechanisms they will promote. However, it's not exhaustive, and there's also another resource in the activity that I provided for you that has a few more examples that you could add to these different categories. So the first category promotes an E2 reaction, and those are reagents that really act as a base only, and they'll always be a strong base. So if something is a weak nucleophile but a strong base, it will promote a reaction as a base, and because it's strong, it will promote an E2 reaction. Now the examples DBN and DBU are only found in the Klein book, and those are not common strong bases. So you can add a few of these to your chart that are a little bit more common. So NH2 is a common strong base only, as well as tert butoxide. So that could be sodium tert butoxide or potassium tert butoxide, which basically looks like this. It's an oxygen with a negative charge, and instead of an ethyl or a methyl group, what's attached is a tert butyl group. That typically goes in the strong base only, just because it's so bulky that it is unlikely to participate as a nucleophile in an SN2 reaction. Reagents such as hydroxide, methoxide, and ethoxide are considered both a strong base and a strong nucleophile. Because it's a strong base, it can promote E2, and because it can react as a strong nucleophile, it can promote SN2. So it's good to know that it can do both of those, and we'll get more than one product. However, then the next step will be, of course, predicting what will be the major product. And that will come in when we analyze the structure of the reagent as the reactant as well. So is it primary, secondary, or tertiary? That will affect whether or not SN2 or E2 is major. For now, just knowing the function of the reagent will at least help us narrow it down. So if we're using something that's considered a strong base and a strong nucleophile, just note that it could potentially promote SN2 and E2. And we would have to further analyze the structure of the alkyl halide to know which one of those two would be the major product versus the minor product. Okay, then the next category of reagents are those that are weak bases, but strong nucleophiles. So those are primarily going to promote substitution reactions because they're acting as better nucleophiles than bases. Now, commonly, this would be an SN2 reaction, but not in all cases. If it was a tertiary substrate, it can only react in an SN1 mechanism. So just for now, On the activity, this category would be called nucleophile only, just because it's a weak base, so it's not likely to act as a base when it can function as a much stronger nucleophile. And that it can promote SN1 or SN2, and again, the exact mechanism will be determined based on the structure of the alkyl halide. And then the last category is weak base and weak nucleophile. So these promote both SN1 and E1 reactions because they are considered weak in both categories. They promote the unimolecular reactions where the base or nucleophile is not involved in the rate determining step. And again, whether or not E1 or SN1 will be major is determined by other factors, such as whether or not the reaction is heated. Okay, so after you've analyzed the function of the reagent and you found it to be in one of those categories, Klein lists them this way, but again, in the activity, they're listed as base only, which by definition is a strong base. So you could call that strong base only. Strong base and strong nucleophile. Nucleophile only. And weak base / weak nucleophile. So again, the next step is to analyze the substrate. Is it primary, secondary, or tertiary? And then there's even additional ones like allylic and benzylic that are not included in this particular organizational table. So if it's a base only and it's a strong base only, then it will promote E2. And E2 is not as picky in terms of the substrate. So primary, secondary, and tertiary substrates all react with a strong base under E2 conditions. If you have a reagent that can function as a strong base and a strong nucleophile, again, examples of those are sodium hydroxide, sodium methoxide, and sodium ethoxide. And I think there's even a couple more examples on the activity that I've added for you. Then it does matter definitely the structure of the alkyl halide. If it's a tertiary substrate, it will only undergo E2, because recall that SN2 reactions do not operate on tertiary alkyl halides because of steric hindrance and the backside attack requirement. Even on secondary substrates, SN2 reactions are fairly slow. As a result, E2 typically predominates. However, on primary or methyl substrates, SN2 reactions are very fast, and they often outcompete E2 reactions. So basically, if you were just looking at major products, you would make mention of SN2 for primary substrates and E2 for secondary and tertiary, but knowing that there's mixtures of products if the substrate is primary or secondary. What if the reagent functions as a nucleophile only? Then it's going to do some sort of substitution reaction. If it's a tertiary substrate, it can only undergo SN1 because, again, tertiary substrates do not undergo SN2 reactions. However, primary substrates undergo very fast SN2 reactions and do not undergo SN1 reactions. This category is a bit in debate still. There are still different opinions on whether or not secondary substrates can react via SN2 and SN1 mechanisms, or just one of those two mechanisms. For now, we'll just say that this could go SN2 or SN1 potentially, depending on how strong the nucleophile is. It can lean towards SN2 more than SN1. And then the last category, again, the weak base, weak nucleophile, those are neutral reagents like water, methanol, and ethanol. Those favor tertiary substrates because those are the ionization step is rate determining, and tertiary carbocations are the most stable. And so those are the only ones that really occur with an appreciable rate. And those give a mixture of SN1 and E1 products. Again, which one is major can depend on the structure of the alkene product, how substituted and stable it is versus the substitution product, and whether or not the reaction is heated. Now in Klein, they give a nice big X over secondary substrates because they tend to be slow reactions and therefore can not produce very high yields of product. Whereas sometimes it is possible if you heat, especially if it can also undergo rearrangement, it is possible to get the product. So this one is kind of also, I would say, a little bit in debate. We may get SN1 and E1 products, we may get a lower yield, or we may have to heat it, which would promote E1. Primary substrates are really slow to react with like water or ethanol. And again, you would have to heat it quite a bit, and it's better if there can be a simultaneous rearrangement to directly form a more stable carbocation. Okay, so after you've analyzed the reagent and the substrate, and you determine which mechanisms will occur, which may be one or more than one, then the next step is to draw all the possible regio and stereoisomers, and then choose the major product using the guidelines that you have learned. Let's go through each of the mechanisms individually to remind ourselves about the regio selectivity and the stereoselectivity of that particular mechanism. This is sort of a bullet that sort of highlights what's written down here in a shorter fashion, but we can read through both of these. So for SN2, recall that we will observe a single product, which typically occurs through inversion of configuration at the alpha carbon. So sometimes the R to S or S to R priorities change, and so we haven't technically got inversion of configuration, but it still occurred through backside attack. And again, it's stereo selective for that inversion product. So for E2, right, recall that we need to draw all the possible alkene isomers. Those might be constitutional isomers, and those might be stereoisomers. So E2 reactions require a anti-periplanar transition state with the beta hydrogen and the leaving group all in the same plane for the reaction to occur. And regioselectively, the Hoffman product is major if a bulky base is used, and the Zaitsev product, which is the most stable alkene, is major if a non-bulky base is used. For SN1 reactions, we need to draw the carbocation intermediate. Consider if it will rearrange. If not, attach the nucleophile to the carbocation at its original location. If it does rearrange, then we need to attach the nucleophile to the carbon where the positive charge ended up after the rearrangement. Typically, stereoselectively, we get a racemic mixture of R and S products if a stereocenter is formed in this reaction. Draw them both, although sometimes there's a slight preference for inversion due to the intimate ion pair. For an E1 reaction, again, just like SN1, we need to draw the carbocation that's formed from the loss of the leaving group. Consider rearrangement. If it's going to rearrange, draw the rearranged carbocation. Then identify all the beta carbons that have a hydrogen attached to them to figure out how many different possible alkene regioisomers can be formed. Also consider stereochemistry. Cis and trans / E and Z stereoisomers can also form. The major product will be the most stable alkene, which is the Zaitsev product, and also typically the E or trans alkene. So let's do a practice problem where we're going through all of those steps. So the question is, predict the products of the following reaction and label the major product. So what we want to do is step one, start with the function of the reagent, sodium hydroxide. Sodium hydroxide is both a strong base and a strong nucleophile. So E2 and SN2 reactions will be favored. Then we'll look at the substrate. It is a secondary alkyl halide. So both SN2 and E2 will occur with secondary substrates, but E2 will dominate because the secondary substrate is still somewhat hindered for backside attack. Now that we know that SN2 products are possible and E2 products are possible, we need to start drawing those products. For the SN2 product, remember that backside attack gives inversion of configuration. So as we replace the leaving group with the incoming nucleophile, we also want to make sure to show inversion of the stereocenter. For the E2 products, remember that an anti-periplanar transition state is required. So only hydrogens that can get in that configuration opposite the leaving group could be removed to form the alkene. If there's only one hydrogen at a beta carbon, then you would need to draw a Newman projection to figure out if the E or Z alkene would be formed. In this case, the alpha carbon is a chiral center. However, the beta carbons are not chiral centers. So we don't have to draw a Newman projection in this particular case. However, we do want to draw in all the hydrogens at the beta carbons to figure out what alkenes are possible. If we remove a hydrogen that's labeled HC, we will end up with the product that's listed last here. That's the Hoffman product. And because this is not a bulky base, this will be one of our minor products. We could potentially remove either HA or HB, and those would give us the two different Zaitsev elimination products. And because it's anti-periplanar to the leaving group, we'll end up with both the E and Z isomers. Recall that E is always favored because it's more stable, less sterically hindered, and if possible to form that, and it will be possible because, again, there's two hydrogens here, not just one. Now that we have drawn all of the products, and we know that E2 is the major pathway and SN2 is the minor pathway, we want to choose one of the E2 products as the major product. Recall that since this is not a stereospecific E2 reaction, because the beta carbon is not a stereocenter, we will form the most stable alkene, both Zaitsev and you can think of it as E or trans. So this is just one example of going through those steps to predict products and identify the major product. You need to do many more examples. There's a bunch of examples on the activity today, and you can do more practice in your book. And I really encourage you to do this because there is no substitute for practicing this process. And this is something that there will be lots of questions on your next exam. Let's talk about some synthetic strategies. I showed this slide before, but I wanted to show it again so that we can talk about it in a little bit more detail now that we've talked about all of the different substitution and elimination mechanisms, all four options that we have. So previously we talked about with a primary alkyl halide, SN2 reactions are very fast. So you can see there's 1, 2, 3, 4 different examples of SN2 reactions here to give different products. Notice the functional groups are labeled. This is our first introduction to really making different functional groups, starting from an alkyl halide. If we treat with sodium cyanide, we can get a nitrile. If we treat with sodium acetate, we can get an ester. If we treat with sodium thiol, we can get a thiol. And if we treat with sodium methoxide, we can get an ether. We can also use sodium hydroxide to give us an alcohol, and that's also an SN2 reaction. We know also in this chapter, we learned how to convert alcohols into alkyl halides. The alcohol OH group is a bad leaving group, so we have to treat with an acid to do an initial proton transfer to make a good leaving group, and then the bromide can come in and do an SN2 reaction to give us our alkyl halide. So interestingly, we've learned a way to convert a primary alkyl halide into a primary alcohol and a primary alcohol back into a primary alkyl halide. Tosylation was also introduced in this chapter, which is a way to convert an alcohol into a good leaving group. And that is typically useful for either SN2 or E2 reactions, where we need a good leaving group. This is an example of an E2 reaction with a strong bulky base, giving us an alkene product. And here's another example of an E2 reaction directly from the alkyl halide, either using a small base or a bulky base. Both of these are strong bases. We can get to the alkene product. Notice that in this particular case, we don't have to worry about regioselectivity because there's only one beta carbon. We can just use either of these and give us the same alkene. Let's look at how the reactions would differ with a tertiary alkyl halide. With a tertiary alkyl halide, recall that we cannot do SN2 reactions. We can only do SN1 or E1 or E2. So those are the different substrate reactions that can occur on a tertiary substrate. Some of these examples are E2 reactions. For example, sodium hydroxide and potassium terbutoxide. These are both strong bases, so they can promote an E2 reaction. This one is bulky, giving the Hofmann product as the major product. Sodium hydroxide is a small, strong base, giving the Zaitsev product as the major product. Alcohols, we can still use the reactions to go from an alkyl halide to an alcohol and an alcohol back to an alkyl halide. With a tertiary alcohol, we can convert that back into a tertiary alkyl bromide, also with HBr, similar to the primary alcohol to the primary alkyl bromide from the last slide. The difference is with the primary substrate, the mechanism is SN2. With the tertiary substrate, the mechanism will be SN1. And it's additionally SN1 to go back to the alcohol with water. Okay, concentrated H2SO4 is used on alcohols to do E1 reactions. And the E1 always gives the Zaitsev product as the major product. Alcohols, even tertiary alcohols, can be tosylated to obtain a good leaving group. And then from there, we can do an E2 reaction, either again with our small strong base or our bulky strong base. So these are all really important reactions that you have to know. You need to remember these reactions in order to predict the products and eventually do what are called multi-step synthesis problems that will be introduced it slightly before, and as we go through the chapters, we'll be introducing it and expanding on that concept quite a bit. So again, these are all really, really important reactions that you need to know. I encourage you to make flashcards to study so that you will know which reagents promote which reactions and predicting the major product. All right, that is enough for today because I really want you to spend the bulk of your time practicing the concept of predicting products by doing that 3-step process that we talked about.